Alright, another draft physics presentation, or draft science, however you like it. YouTube, draft science, on the web, draftphysics.com. Anyway, not a necessary clarification probably. So anyway, some guy, anyway, posted a link, really good, so we'll play it. Here we see it doesn't fall when it's kept upside down. So this is the quantum locking thing, which is really just gravitational locking, as I'll point out again. It would be impossible for your, whatever that means, activity to not create also wrongs. That's the only scientific method. And opposed to the Feynman, one of the Feynman lectures, which I've seen more than any other human on Earth, I believe. It just doesn't mean anything. Keep it tough and focus also on one thing to make it big. I don't know what the hell he's talking about. Pleasure comes with its reason. This message will auto-destruct in 5 hours. Apparently 5 hours, 5H, I don't know. 5 histograms, I don't know, 5 Huygenses. So apparently the guy's crazy, but at least the link is worth something. So we'll go to the link. But yeah, don't need that music. Annoying.
So what if we got here?
So we have quantum locking. The superconductor is locked in space. And it's
Alright, so again, they call it quantum locking, but clearly we all know that gravity is the only force acting on it. So we know there's this force acting on it. Gravity is acting on it. And so we have to account for gravity as being the force that's acting on it. Now, you can see the magnet is a composite. So what's probably engineered into the magnet is the fact that they want the field to keep the thing from sliding off. So there's probably some reason that it's in pieces like that, and it's probably to keep it the field a little bit uneven. But anyway, we'll move on.
It stays wherever I put it. You see, this is quantum trapping.
So again, they call it quantum trapping, but again, we know the only force acting on it is gravity. So whatever's happening is clearly anti-gravity in that sense. It's creating a pure reflection of gravity and preventing gravity from acting on the piece of crap. So the piece of crap is the total system somehow is saying there's no gravity in the sense that it's undoing it. It's creating an opposite force that's exactly equal to the gravity, just as I stated before.
That's amazing.
As long as it's
so it's superconducting. It's frozen with liquid nitrogen.
Upside down.
Right.
And it stays locked.
So the fact that it's superconducting is locking the magnet.
Right. So I was wrong to say that if you tipped it over it wouldn't work. So again, I didn't do any research. I was just going back on what I saw 5 years ago in terms of a demonstration of this effect. But again, in my opinion, there's nothing mysterious beyond what Maxwell's equations could tell you in a sense. This is just about the fact that in the superconductor you're eliminating all the system noise that makes it impossible to happen at regular temperatures. So you're just getting rid of the delay, the imperfection, so to speak, in Lenz's law. So if you apply Lenz's law in a perfect system, this is what it would look like.
Magnetic field in 3 dimensions, right?
Yeah, exactly.
And that's
and
pivots.
You see, because this is symmetric, it can rotate without break the locking. The locking doesn't break.
Right.
Because
so in this position he couldn't tilt it, I guess. I guess that's why the other magnets are in pieces, is to make the tilting thing more possible.
But it stays there on the X and Y, but not on, it pivots on the...
on the axis of the magnets. You see, if I can move it on the side, it will again pivot around it.
Right, so but he just can't turn it sideways now. So these are just the rules of the different composite magnets will give you different effects. But the bottom line is it undoes what gravity should be doing to the object.
The axis of the magnet, because it makes sure that the magnetic field inside of it stays the same.
Right. It's astonishing.
So again, it's the magnetic field still is exactly compensating for gravity. So again, the thing to be constantly aware of is that we know the one force that does exist is gravity. Now we know that gravity can't just be undone, you know, with nothing. So there has to be something that's exactly compensating for what gravity would be doing to the object. So whatever it's doing to the object is exactly the same amount of energy as what gravity is doing. So gravity's 10 meters per second pushing down on it, and somehow the board with the magnet on it is pushing back up at it at 10 meters per second. Now it's not pushing in the same, it's not hitting the same surface, it's not hitting all that stuff, but wherever it is hitting, it's hitting with exactly that much force. So the thing, if the thing moves towards the magnet, the magnet creates in the object, because of the change, it reacts to the change and it pushes against the change. So the thing is probably micro vibrating. I mean, we don't see the Brownian motion, but there's probably Brownian motion. It's vibrating on that surface. And so any changes means that it gets the opposite reaction from the material. Material keeps opposite reacting. So if you push it away, that's reducing the field. It's still a change in the magnetic field. You change the field, it's reacting by increasing the attractive force or diminishing the amount of force affecting it. And so that allows it to fall back down. And if it was reversed upside down, it would be exactly the opposite effect. Because the gravity's pushing down, it's pulling back up.
Can you put it on the track for us?
Yeah. I just levitated above the track quite high, and I can just rotate it.
So it's actually floating above the surface.
Yeah, it's not floating, it's locked above the surface.
So it could, you could tilt it at an angle and it would still fly
I can do
around.
it like this, and it will just go around like this. Because I go and put it at different height.
I wonder how much speed they can actually give it before it flies out, though. So again, it's all engineered for the purpose of the demonstration. So we're not being shown its limitations. We're just being shown, you know, the fun part.
And then like this.
You lock it at the height.
Lock
right?
it, yeah, different height, different configuration.
Right.
And I can even lock it at opposite way. If you could just hold for a minute. Hi. I'm doing the same thing. I'm locking it upside down, and then.
And so again, as the object falls from the gravity, okay, that's the field it's feeling is now diminishing. The field is reducing, and as that field reduces, it creates the opposite field to that response. Now it becomes attractive, and it pushes itself back up towards it because it becomes the opposite charge, and says, I'm opposite charging as I fall. So I'll go back up because I'm being attracted as I'm opposite charging. So as it falls away from the magnet, its mirror effect starts reducing. All right, so now it's becoming attractive because it's changing its polarity as it falls. And then as it moves back up, if it gets too close, then the same thing happens. And it's like a perfect mirror. So if you do place it in one place at any one position, because of the, whatever you want to call it, the straight line force, it's essentially a straight line force, and again, it's always going to compensate for any movement. So even if you made it into a ball, you could probably get away with this, you know, in the sense that it would still float, because the just trying to think of the symmetry argument. Yeah, I shouldn't speculate about stuff I can't say for sure. But theoretically, I'm just arguing that the argument is no matter how much exposure the surface has to the magnetic field, doesn't matter, because as long as the thing keeps falling, this strength of the field, the conversion of this into the opposite field will keep getting stronger. So as it falls, there's going to be a point where it's just going to be so opposite that the two things have to attract again. So it's always going to balance, attempt balance. So the interesting part would be, you know, playing with full contact with the surface, and then what's the furthest distance where it lets loose. You know, that first attachment, does it pop into that position? You know, some things like that might be interesting to see. So anyway, good video.
It is suspended.
Fantastic. Okay.
All right. So, and again, the position thing just means that essentially the atoms are all acting on their own. That's part of the fact that it's such a perfect conductor. That's not the word you want to use. The atoms are all reacting as individual little atoms. They're either saying I'm positive or I'm negative, and that's why you can move it into any position. It's because one side doesn't really care what the other side's doing. They're all individually acting as atoms. Alright, so I don't know, do I need to draw it? Or maybe I'll draw something. Just to make the video a little bit more complete, I suppose. So let's see, how to actually, I mean, so it's just Lenz's law. You don't need to call it quantum locking or any of that crap. And it's just Lenz's law in a perfect system. So the idea is that this object, the field hits it, and if it's you know, blue energy hitting it, it responds with blue energy, so to speak. Okay, so there's an equal response to what it's being hit by. So whatever hits it, it's going to respond in kind in terms of the percentages. So what has to be understood is it's really a mixed field in the sense there is red, all right, and it's a percentage. All right, the percentage could be 60-40, doesn't really matter. And so as the balance changes, the material responds to meet that balance. So whatever this changes to, if I make this 42-58, okay, 58 blue just to imply the density of the material, the concentration, then this will respond in kind, okay, and become 58, you know, 48, I did some 52, 42, yeah. And so it'll always create an even tension to whatever change you make in the field. It will change this other surface to meet that change. And the point would be is this, I shouldn't really use these percentages, because all it really would matter is, even if only one part of this thing, like I said, I slid this all the way over here. So yeah, let's redraw it that way. That's a better way to understand it. So if I had the magnet here and I slid this material over here, well, obviously I can't hang it over too far over the edge. So I'm doing, this is a bit of an exaggeration. But the idea would be is this contact is all there needs to be for the movement to still be felt. So you'll still feel the movement down, and the change in the field will still be the same as far as it's concerned for this part of the material. So this part of the material is going to feel the change in the field, that they're still moving, and it's saying I don't want to move, essentially. The reaction is to stop the movement. The reaction is this field's going to become more red, okay, the further away this thing moves, and it's going to become more blue the closer it gets. And that's all that's going to matter. So if it keeps moving, it's going to get bluer and bluer and bluer. So if it moves towards the blue, it's going to get bluer and bluer and bluer. If it starts moving away, it's going to get redder and redder and redder. So it constantly is compensating for the movement. So it doesn't matter how much of it's really exposed, it's going to consider this whole weight as its weight. Now obviously if it was way tilted this end will probably tilt down and the whole thing will not work. So you have to have at least half of it over the magnet for it to levitate. And again, this material is really light, so let's Now let's understand, it's not like it's a heavy piece of metal. It's a light composite material. So anyway, so yes, it doesn't matter if it's upside down or right side up. Is what it's acting, what it's reacting to is the movement created by gravity. Gravity is the source of the movement, and it's just reacting to compensate for the movement. The field inside of it changes as you move. So if I move the thing up, the thing's going to move with it because there's a change in the field, and it's going to react to the change in the field. It's just going to keep reacting to the change in the field. Let's see, is there any other way to say it? So that was the one part he didn't show, I guess. Let's see if we see that in the video. How much he moves the... Well, he turned it upside down, and it stayed pretty consistent. So that's pretty good evidence right there. What happened to the... Oh, there it is. So when he turned it upside down...
Upside down,
right,
and it stays locked.
So the fact that it's superconducting is locking.
All right, so it's the speed is which he's turning it. So if he turns it, theoretically, if it turned it real fast, it's still just going to rebound. It's still going to just keep reacting. I mean, it can react faster than your reflexes can probably react. So you probably can't move anything faster than the field can change to compensate for the movement. So if you try to move the bottom plate up into it, you know, jerk it off, flip it off, it's going to stick because every time you move the thing up, you're changing the field again, and it's just going to move the material to compensate for the movement you made, because it's going to change it's going to become blue again. Blue on blue is going to mean repulsion. So as you move into it, it turns blue, it repels, so it's just going to move whatever movement you impose. So the only force it's compensating for, the only force acting in the system to initiate the response is gravity. So gravity is the initial act. The counteract is the creation inside of the material of its polarization changes as you move the magnetic field into it. As the magnetic field gets moved into, the gravity pushes it down, let's say. The magnetic field is hitting it, it gets stronger. This turns red, if the magnet's red. I don't want to make things even more confusing. I mean, I can't make this pen turn red by moving it close to the red, but the point is as it gets pushed down, it turns red. That causes it to repel. So whatever movement there is, it acts against that movement. So it's just Lenz's law. I'll say it again. It's just Lenz's law perfected in an ideal state. So Lenz's law in ideal circumstances does this. That's probably the right way to say it. An ideal version of Lenz's law looks just like this. You don't need the word quantum. Complete bullshit. Okay, enough of the video. And such. Yeah, hit the button.